Welcome to our channel, and today we are going to help you understand the paper Introspective Tips Large Language Model for In-Context Decision Making. The text provides an overview of a study that examines the use of introspective tips to improve decision making in large language models, LLMs. These LLMs, such as OpenAI's GPT 3.5, GPT 4, and Google's PaLM, have shown impressive performance across a variety of natural language processing tasks. The study aims to enhance LLM's decision-making abilities without altering their parameters. Instead, it focuses on refining their prompt to extract valuable insights from agent experiences, expert demonstrations, and a variety of games. The authors adjust the decision-making process of LLMs in three critical situations: when learning from past experiences, incorporating expert demonstrations, and generalizing skills across diverse games. In doing so, they leverage the inherent common sense knowledge and training of LLMs to overcome typical decision making challenges such as sparse rewards and other potential decision making pitfalls. Despite the considerable abilities of LLMs, they can sometimes produce errors or hallucinations in their outputs, especially in domain specific contexts. To counter this, the study introduces self-correction mechanisms that allow the LLMs to critically evaluate their own decision-making processes and generate concise, helpful tips to self-optimize. This introspective approach leads to improved performance by the agents in both few-shot and zero-shot learning scenarios. This methodology is showcased in over 100 games within the text world environment, demonstrating significant advancements over previous approaches. It emphasizes the benefits of utilizing LLMs for in-context decision-making, providing a framework that supports improved decision-making capabilities in AI agents. The text discusses different approaches to reasoning within artificial intelligence systems. Chain of thought, COT, focuses on one-step static reasoning without self-correction. Subsequent works, React and Reflection, introduce dynamic reasoning, which uses past interactions for better decision-making, but are tailored to specific agents, limiting generalization. Traditional reflection does not correct errors, potentially impairing decisions. Humans have strong generalization skills and self-evolution abilities based on introspection, the capacity to learn from experiences by reflecting on them. Building on this human skill, the authors propose a new method called introspective tips to enhance the decision-making of large language models, LLMs. The method enables an LLM agent to self-optimize by learning from its own experiences, as well as those of experts and various environments. The example given involves a text-based game where the agent must cook meals using two different cookbooks. After completing Game 1, the agent uses tips from that experience to successfully apply general cooking knowledge to Game 2. In contrast, when using specific reflections from Game 1, the agent fails Game 2 due to irrelevant advice about potatoes. Tips, which are broad and high level, are shown to be more effective for general guidance and improving the agent's performance than Game 1 specific reflections. The ultimate goal of tips is to provide helpful, succinct advice that aids in generalizing experiences to new situations. The text discusses a decision-making framework for language learning models, LLMs, aimed at enhancing performance without requiring the analysis of past trajectories. This framework introduces the concept of introspective tips, which differ from reflections in that they can be derived from the agent itself as well as from other agents and human experts, learning from both successes and failures. The document highlights several points. Introspective tips provide condensed insights from lengthy trajectories, helping LLMs identify complex relationships between actions and rewards. These tips are applicable and generalizable across different agents and contexts, whereas reflections are more specific to individual trajectories. The framework can be used in various scenarios, showing flexibility and adaptability. It includes a dynamic prompt adjustment feature that uses insights derived from introspection to facilitate the generation of introspective tips. This new approach does not require retraining or fine-tuning, offering an end-to-end solution that produces easy-to-understand tips and allows for easier human intervention in decision-making processes. The framework's efficiency and adaptability are further supported by comprehensive evaluations that include over 100 games in TextWorld, with comparisons against state of the art methods, showcasing its effectiveness in both few shot and zero shot learning scenarios. The text discusses the use of large language models, LLMs, in decision making tasks and how they have been effectively applied in various studies. The introspective tips method, where tips generated from a relatively small number of trajectories, enables an LLM agent to outperform traditional deep learning methods trained on a much larger dataset when tested in a difficult, unseen game environment. The effectiveness of LLMs as decision making tools is further shown in studies that teach them to perform intermediate reasoning, act on interleaved reasoning and actions, self reflect, offer feedback, and learn from human feedback. Additionally, LLMs can be used in decision making without relying on language as input or output through prompt engineering and functioning as part of a larger system that includes low level reinforcement learning agents and proxy reward functions. LLMs have also been proposed as world models, enabling agents to learn policies by interacting with these models. The paper goes on to focus on the direct application of LLMs in making decisions to take actions, which is seen as more sample efficient than methods that require learning an additional decision making agent. The concept of in context learning for reinforcement learning is discussed, referring to models that adapt to new downstream tasks through prompts without retraining. Several studies have recast reinforcement learning as sequential prediction problems and have used LLMs for planning and in context action execution. Some work also involves developing algorithms that allow RL agents to adapt as rapidly as humans to new and open ended 3D challenges by training them at a large scale. The text is detailing advancements and ongoing research efforts that leverage LLMs to enhance decision-making capabilities in various computational applications. The text discusses the application and challenges of using deep learning models, specifically language learning models, LLMs, and generative pre-trained transformers, GPT, denoted by Gato in the text, in text-based games. These games are played through text commands in a command line interface, with game states described by text and are characterized as partially observable Markov decision processes because players have limited information at each turn. Inherently difficult due to factors like partial observation and sparse rewards, several deep learning approaches have been explored to tackle these games. The Gato model is mentioned as being able to generalize to new tasks by learning from demonstrations. It builds upon prior research that utilizes graph structures for representing states and updates this knowledge to optimize rewards. Subsequent work by Tully et al. Improved upon this by adding the capability to parse natural language instructions using linear temporal logic, aiding in the understanding of tasks. The methods section of the text elaborates on using LLMs in sequential decision-making tasks, capitalizing on their strengths in text processing while addressing their limitations, such as lack of specific domain knowledge. By using the vast function space of LLMs and the right prompting strategies containing domain knowledge, a model can be derived that functions effectively in decision-making, thus combining LLMs with principles of reinforcement learning. Moreover, the text identifies challenges in using LLMs for decision-making problems: self-optimization, input length limitations, and prompt dependence. It suggests that by learning from past experiences and expert demonstrations, and by applying knowledge across multiple games, a versatile framework can be developed for LLMs, enabling them to excel in various gaming scenarios and unlocking their potential in complex, sequential decision-making tasks. The text discusses challenges and proposed solutions relating to the decision-making performance of self-optimizing large language models, LLMs. These models can make errors or hallucinate, especially in domain-specific contexts. There's an emphasis on the need for mechanisms that help LLMs correct their mistakes, which is vital for enhancing their decision-making. One approach that is touched upon is the concept of self-reflection, where LLMs focus on their own errors to try and fix them. However, this method can be limited, as models might be misled by their own mistakes and may not fully understand the task or environment. To overcome these issues, the use of introspective tips is proposed, which helps LLMs self-optimize by learning from their own actions, expert demonstrations, and experiences in different environments. Using these tips, LLMs can gather concise, actionable advice and overcome problems with hallucination. The text also addresses the challenge posed by input length limitations found in advanced language models like GPT-4 and Palm. When interacting with complex and lengthy information, LLMs struggle to understand the connection between actions and delayed rewards, which hinders optimal policy learning. To remedy this, the authors suggest using tips that condense essential information to optimize input space. This allows LLMs to better understand data relationships and is useful when learning from limited datasets or adapting to new situations. Furthermore, the dependence of LLMs on the quality and order of prompts is a significant factor in their performance. The text then goes on to describe a method that involves dynamically adjusting prompts based on past experiences, which helps streamline the process and makes LLMs more adaptable. The prospect of creating a universal prompt that would enable efficient reinforcement learning across various games and contexts is also explored. Finally, the basic setting described employs an LLM as an agent in a text-based game, highlighting an example of how such an interaction is carried out. The text provides an overview of an LLM language model as an RL, reinforcement learning agent, within a text-based game scenario. The agent receives actions from an action list, and the user, referred to as the system, provides a description of the game's environment. The LLM agent's task is to interpret this information and decide on a single action to take, communicate it back to the system, and then wait for a response, which could include updates on the game environment or feedback on the validity of the action. The game proceeds with the agent selecting actions and the system providing new information until the game ends, either in success if all tasks are completed, or in failure due to incorrect actions or reaching a turn limit. In Section 3.3, strategies are discussed to help the LLM agent learn and improve from its experiences. One such strategy involves the agent using history replay, where it generates self-improvement tips based on its past actions, mainly focusing on past failures. These tips then act as prompts in subsequent attempts. If the agent fails even with these tips, it must create more effective tips. The agent's previous failing actions are provided to assist in this reflective learning process. The text discusses a method where an agent improves its performance in text-based games by learning from its actions and outcomes and by comparing its performance with expert demonstrations. The agent refines its policy by generating insights that help it overcome obstacles and make better decisions in future gameplay. Unlike relying on its past experiences alone, the agent benefits from a richer history by learning from shorter tips and incorrect actions, which help it to progress faster. To further improve performance, the agent observes the actions of expert players, identifying both their successful strategies and the mistakes they made. This allows the agent to focus on areas for improvement and apply tips to adjust its behavior. This type of learning is more efficient than trial and error, because the agent can learn from the contrast between its unsuccessful attempts and the expert's successful actions. Rather than testing every possible action, the agent also learns from multiple games, extracting final successful tips, which are then processed by another LLM to generate general tips. These tips can be applied across various game settings, even when some game components differ. The LLM effectively becomes a meta-RL agent, applying generalized knowledge to new, unseen games. The text also mentions an experimental framework that evaluates the LLM's ability to learn from history, expert demonstrations, and multiple games, posing questions about the LLM's capacity to improve by reflecting on different tips and learning from expert demonstrations. The overarching goal is to demonstrate the flexibility and effectiveness of LLMs in learning and adapting within reinforcement learning environments, particularly in text-based gaming contexts. The summary of the given text is as follows. The text discusses an experiment concerning the performance of large language models, LLMs, in few-shot and zero-shot decision-making in the context of text-based games. In particular, the study looks at how LLMs perform after being exposed to a small number of game demonstrations across different levels of difficulty, and inquires whether expert demonstrations could improve the model's learning of various strategies, Q1 and Q2. As for Q3, the focus is on the LLM's ability to generalize tips and play effectively in different game scenarios without prior specific examples, zero-shot decision-making. Experimentally, the research zooms in on the text world cooking domain, a text-based game environment used for studying language understanding and decision-making in AI. This environment has been highlighted in previous works by Adhikari et al. 2020 and in a challenge proposed by Microsoft. The experiment's setup is detailed in a table that lists statistics about the game levels, including the number of ingredients, locations, and points associated with different actions like cooking, cutting, and opening within the game. The symbols indicate whether an action is available or relevant within a particular level. The experiment setups range from simple scenarios with only one type of action possible to more complex ones with multiple locations and actions available. In the study by Tooley et al., 2022, the researchers classified text-based games into 5 categories based on difficulty. Simpler games require less navigation and ingredients for the tasks, while more difficult games challenge the agent with multiple rooms, navigation, and cooking tasks with various steps. Performance metrics include normalized game points and game success rates, basing results on 20 games at each difficulty level. The paper examines the few-shot performance of agents, comparing 3 methods: replaying past trajectories, using a tip summary from past history, and comparing to expert trajectories. The latter 2 represent different scenarios in the study. The maximum trajectory input is capped at 3 for replay scenarios. Agents with tip summaries performed better, with high success rates and points after cumulative trials. Expert demonstrations resulted in more efficient learning, with agents achieving perfect scores after 6 trials maximum. The findings suggest concise tips can guide the learning language model, LLM, to gather information and make better decisions, while expert demonstrations further enhance learning efficiency. An example provided shows the agent learning to roast a potato through trial and error. Only after incorrect attempts with a stove and invalid actions did the agent realize using an oven was the correct method, leading to success in the 4th trial. This indicates that adapted tips and learning from errors contribute to successful completion of the game tasks. The text discusses an experiment that evaluates the performance of a language model, LLM agent, in a cooking-related text-based game. The agent is given tips to improve its actions across multiple trials, with the goal of learning to cook a purple potato using the correct method. In the first trial, the agent incorrectly fries the potato when instructed to cook it on a stove. It is then advised to roast it instead. Despite further trials and corrected actions, it isn't until the 4th trial, when following the advice to cook the purple potato in an oven, that the agent successfully roasts the potato and improves its score. The experiment focuses on enhancing the LLM agent's proficiency by providing it with successful tips derived from challenging games in the training set. These tips are then tested across different difficulty levels in an unseen test set. The LLM agent, prompted with general tips, achieved comparable results to state-of-the-art SOTA deep learning game agents for easier difficulty levels 0-3, and it outperformed other methods at higher levels 3-4 due to its reasoning abilities and the effective use of tips. However, the agent did underperform in some lower difficulty games, where it failed to generate a general tip suitable for specific situations. This indicates that despite its successes, the LLM has limitations that affect its performance in certain contexts. The text discusses a method for improving the performance of language model LM agents in text-based games by using introspective tips. These tips are human-generated instructions that help the LM make better decisions. When followed, the tips lead to significantly higher scores and success rates, as shown in Table 2. However, due to the probabilistic nature of the LMs, they might not always follow the tips, resulting in occasional mistakes. The text states that even though LMs can behave unpredictably, an LM with general tips still has better performance than state-of-the-art SOTA agents specifically trained for these tasks. Although data for certain difficulty levels are missing, comparisons from other studies are used to demonstrate the effectiveness. The summary concludes with the concept of introspective tips, which empowers LMs to self optimize by learning from broad, general information gained through introspection and by adjusting prompts dynamically. This method not only reduces the effort needed to manually craft prompts, but it also takes advantage of LM's common sense knowledge and generalization skills. The LM agents using introspective tips outperform SOTA methods in the text based game. The article suggests that future work may include improving the framework for generating prompts, finding better ways to extract tips, and testing the effectiveness of the tips in a wider variety of tasks and applications.